All right, welcome everyone to my session. Today I'm going to talk about the building Zephyr for MicroBlaze RISC-V FPGA using Yocto Project. About me, I'm a Yocto Project architect at AMD, formerly Xilinx. I'm using Linux since 2006 and Open Embedded since 2010. I'm a contributor to Yocto Project meta layers, Open Embedded, U-Boot, Linux, and lopper. I'm also the co-maintainer of meta-Jupyter and the meta-Xilinx Yocto project layer. So in today's session, we're going to talk about some introduction about the MicroBlaze RISC-V processor, System DeviceTree, lopper, Zephyr, Yocto project, and how we use Yocto project configuration using System DeviceTree and lopper to build Zephyr project, and what would be the roadmap for the meta-zephyr layer. So in today's talk, we are covering like three open source components. One is the RISC-V, Yocto project, and the Zephyr. So basically, the Yocto project you can build for like custom Linux distribution for like just not for Linux. You can do it for like baremetal and the Zephyr RTOS as well. And also like Yocto project can be configured for like not just like a single build system. You can configure for like multi-target build system using something called as like multiconfig. And in today's talk, and we talk about like how we configure the multi-config for the MicroBlaze-V, which is RISC-V based FPGA, and we use like meta-zephyr layer along with meta-Xilinx layer, and we use the System DeviceTree and pass through the lopper tool to generate the Zephyr Kconfig, the board DTS, the SOC DTS, and the Yocto project multi-config files for the MicroBlaze RISC-V. And the output of these configuration files will be used as the input to the multi-config build system. This is just a brief introduction about the MicroBlaze, classic MicroBlaze, and recently the FPGA turned 40, and as part of the AMD MicroBlaze devices, it uses the AXI-based, and it also uses the ARM-compatible portfolio IPs, and it also has like custom RISC instruction set, and we do have the custom GCC to build the MicroBlaze. And also it provides the high integrity in the tools, and it is like and also like our Vivado tools provide like simple design methodologies. So the next is the MicroBlaze RISC-V, and this is like built on like classic MicroBlaze, and it also supports like AXI support, the RISC-V ISA implementation compatible with open source GCC, and also the first release it was rolled out in like 24.1, I think May 2024. And these MicroBlaze-V is integrated in the Vivado tools, and it provides like a user to configure different RISC-V ISA configurations in the Vivado. So I'm going to talk about the MicroBlaze-V hardware a little bit here. So MicroBlaze-V is a RISC-V version of the AMD MicroBlaze soft processor. So it is available in most of the AMD devices supported by Vivado, and also you don't need additional licensing for MicroBlaze-V. So the MicroBlaze-V instructions execution is in like a pipelined, so it can be like fetch, decode, execute, and write back, and memory access. Such kind of MicroBlaze RISC-V pipeline staging can be done using the Vivado tools. So in MicroBlaze-V processor, like it can be configured. It is available as a microcontroller, and you can configure as the memory production unit for like physical access, physical memory production. And also it supports the MMU, which is coming soon, and for the memory virtualization. And the MicroBlaze-V can be configured as like RISC-V ISA architecture, and it supports like multiple pipeline length, like 3, 4, 5, and 8 stages. And also it supports the instruction cache and the data cache, which is required for any operating system to run. Next, we're gonna talk about the system device tree. So before that, we're gonna talk a little bit about device tree. Device tree is nothing but an hardware description you write for a particular hardware device. This device tree is the data structure with all the nodes you need to have for a physical device, such as like CPU, memory, and peripheral devices. Device trees are used in like U-boot, Linux, Zen, and Zephyr projects. So in order to load up a bootable operating system or the bootloader, we require the device tree, and it uses the client memory and passes the pointer to the device tree to the client. And usually the traditional device trees are described with like for the only one system with one address map. For example, in case of the system device tree, we define the system device tree for like heterogeneous system, which needs for like multiple device trees for each operating specific environment, such as you can build one device tree and which can be used for like Linux, U-boot, Zen, and Zephyr. System device tree is like open source device tree that is complete for like a heterogeneous build system. Basically, it contains like two things. One is the domains. Domains contain it is nothing but a set of nodes which is defined for a specific address spaces. And next one is the resource group. Resource group is a set of shared nodes which are like grouped together for a particular domain. So also the system device tree can be used for like multiple cluster, CPU cluster. For example, if you are building a device tree for a Cortex A processor, Core 0, and you can build for Core 1, Core 2, etc. And each device tree can be used to build for like particular operating environment. For example, if you build a device tree for like Cortex A Core 0, you can run Linux, and Cortex R Core 0, you can run like baremetal or like RTOS. Next, we will talk about the lopper tool. Lopper is an open source tool which is used to transform the device tree for an operating specific environment. Basically, what it does is it prunes the system device tree for an operating environment such as like U-boot, Linux, Zen, and for the standard device tree operating modes. So this lopper, what it does is basically it merges or removes the nodes and resolves all the system address map issues. The lopper, basically it contains like two main components. The first one we called as like lopper operations, we call lops, and the next one is the lop status. There is a brief talk from like my colleague Bruce Ashfield in the Linaro Summit. You can refer to that slides. So now we have the system device tree. How do we transform that system device to a lopper transformed output? So this is the output of the system device tree, how it looks like. And the lopper has this like the core, and it has like multiple lops, which is like the first three highlighted in green is part of the meta-zephyr layer. Basically, these lops files are used to convert your device tree to like a machine configurations file for Yocto builds. And the next one is the lops for each processor. For example, here we are using the Cortex A78 and the R52 and the MicroBlaze RISC-V and the Zephyr interrupt controller. And the next one is the LOPS assist. What this LOPS assist does is like it takes the system domain DTS and it converts to an operating specific environment DTS. For example, you can pass the system domain DTS and you can convert to like Linux device tree for each specific course, and a Zephyr device tree for like APU, RPU, MicroBlaze-V with multiple CPUs. And also it can convert the LOPS domains for the bare metal and something for the overlays as well to load the programmable logic. And once these LOPS assist modules is converted, it converts to a like Kconfig file, and the board DTS file, and the SOC configuration files. These are the output of the lopper for a Zephyr configuration builds. Next, we're going to talk about a little bit basics of Zephyr. Zephyr is like a scalable real-time operating system developed by like Linux Foundation, and it is mainly focused for like resource-constrained devices, and it also supports like multiple architectures for hardware, and it is like community-driven, and it also like supports the security for the Zephyr operating system. So basically the Zephyr build system has like two phases. One is the configuration phase, which uses the CMake tools, and the next one is the build phase. The build phase uses the makefiles and the Ninja tools. So we are not gonna talk deep dive into the Zephyr project here. We are like mainly focused on what are the artifacts which is required in order to build Zephyr using Yocto project. This is the Zephyr build flow. So you have the application, your third-party modules, and the Zephyr modules, and you have like a core Zephyr. Basically, you need like two components to build Zephyr. The first one is the device tree, and the device tree, again, it can be like your application-specific device tree, your board-specific device tree, and your SoC-specific device trees. And once these device trees are generated using like a Zephyr script DTS, it will be converted to like a Zephyr DTS file, and this basically this DTS file will not be used for the final compilation. It is just used for your configuring and converting that to an device tree preprocessor, and it generates the device tree generated.h, and final the generated device tree will be device tree.h. And this Zephyr DTS is we use for like morely for like converting your device tree into an macros. Next is the Kconfig. The Kconfig can be your like HAPS Kconfig, which is your project CFG file, and it can be your board-specific Kconfigs or your SoC-specific Kconfig. And these Kconfig, when the build is started, it will be merged, and it generates this autoconfig.h and the .config. The .config is the one, finally, which will be used in the Yocto project build system. And also, it generates the make files and the Ninja files, which is required for building the Zephyr applications. Next, we're going to talk about the Yocto project. So Yocto project is an open source project that helps like developers to create their custom Linux-based products, and it is not only just like focused on Linux. It also like focuses on like bare metal and RTOS, and regardless of which architecture you're gonna build. So So this is the overview of the Yocto project. So basically, it has like different components. The first one is the bitbake. Bitbake is a build engine, which means it's a task executor and the scheduler of like open embedded layer. So next is the layer. Layer is nothing but a collection of like metadata files. Basically, it could be a configuration files, recipes, and it is organized into a files and the directory structure. The next one is the recipe. Recipe is the collection of like metadata, which is such as like it has like different tasks and what kind of tasks and what kind of operations you need to run for an bitbake. Next is the configuration files. These configuration files are like global to the build system in the simple form of like variable assignment. If you want to like build a Yocto project, these configuration files are really important. The next one is the machine file. Machine file describes your hardware configuration based on your like processor or your SoC or your like tune files. Some of the Yocto project basics is like the user configuration. Basically, so in the user configuration, you have like two files. The first one is the local.config, and the next one is the bbls.config file. The local.config file is like the global to the build system, and it has like multiple default variables, which is like BB number of thread, parallel makes, and machine distro settings, and the extra image features. So this BB number of thread is the maximum number of bitbake tasks you execute simultaneously. And the parallel makes is like extra options you pass to the make command during the like any of the bitbake tasks, such as like do configure, do compile, etc. And these are like in parallel compilation to the local build system. And also the distro variable is the distribution like configuration file. For example, if you are building for like a Linux distro or a Zephyr distro, this distro variable will be used. Next is the like Yocto project has like a multi-config builds. So basically this multi-config build is like you have a configuration file which can be built for like multiple target build system. For example, here if you look at you have under build directory you have like conf, and under conf you have like multi-conf. In the multi-conf you define like two configuration files. One is like specific to ARM configuration, and one is you can set it for like the x86 architecture. In the multi-config, like specifies like each additional configuration files for your building multiple target systems. For example, if I'm building a configuration file, which also can target for like B configuration files. Next one is this is the basic syntax of like how you use like multi-config builds. Basically, you have like bitcake, you run with the target image recipe, or you can use like a bitbake with MC:MC stand for the multi-config. You specify the multi-configuration name is followed by colon with the target image recipe. And also like you can add like, for example, A configuration depends on like B configuration. For example, if I'm building if I want to run some virtualization on an x86 machine with the ARM processor, first it has to build the ARM images, and then it has to be built with the x86. So that's where we had the task dependencies for the multi-configs. Next, we're gonna talk about the meta-zephyr layer. So the meta-zephyr layer is part of the Yocto project, and it uses the Yocto build system to build all the Zephyr applications. In case of the standalone Zephyr build, it uses the West build, but here in case of a Yocto project, it uses the native CMake tools, Ninja, Python, and other packages in order to build Zephyr. And this meta-zephyr is categorized into like two sub-layers, which is the meta-zephyr core and the Zephyr BSP. The core layer provides all the build tools packages, and it also provides the set of BB classes, which is called like bitpec classes, to configure your project, build your project, and run your project using QEMU. And it also provides the Flash tools in order to program the Zephyr application to your hardware. And also it supports the Yocto project test images. The meta-zephyr supports also layer supports with the, it includes the meta-zephyr kernel source include files and the recipes. And also it includes the sample applications, Zephyr SDK toolchain, and also it includes the scripts to generate the Zephyr kernel and the other repositories such as like modules or the bootloaders. And basically the meta-zephyr BSP layer will contain all the machine configuration files for your hardware and the QEMU. And there is another layer, which is really not a layer. It's basically a script directory, which has like a build and test CI infrastructure using CAS. Next, we're gonna talk about like meta AMD Zephyr. So why we are using meta AMD Zephyr instead of meta Zephyr? So meta Zephyr uses like the standalone, the DeviceTree kernel configs in order to build the Zephyr application. But in case of meta AMD Zephyr, what we do is we take the system device tree and we transform to a like operating specific device trees and kernel config and the port-specific device trees and the SOC configs. We use these configuration files as input to the meta-Zephyr, and we build this to generate the Zephyr applications. And also like meta-Zephyr support, like basically we are talking about like the Yocto Project's ScartCap release. The meta-Zephyr doesn't provide Zephyr LTS 3 version, which is like 3.0, 7.0. And in meta AMD Zephyr, we have backported the Zephyr 3.7.0 LTS kernel sources and the recipes for the ScartCap release. And it also has like we have backported the Zephyr SDK application for like ScartCap. And the meta AMD Zephyr also includes a kernel source which is like very specific to like Zephyr AMD repository. Basically what it does is like when you start the meta-Zephyr build, it will clone the upstream Zephyr repository and it will start building. When you try to include the meta AMD Zephyr, instead of cloning upstream Zephyr repository, it will clone the AMD Zephyr repositories. And also it has like sample configuration files to build the MicroBlaze-32 boards. Next, we're going to talk about like generating the Yocto project configuration using the system device tree. So in order to generate the system device tree, you need to have like prerequisites. You need to download and install all the AMD Vivado tools. And once you have the Vivado tools installed, you generate a design for MicroBlaze RISC-V. And then you take the design and convert it to generate the hardware description file, which is called as XSA. And once you generate the XSA, we run a tool called like SDT-Gen. And what this tool it does is like it's a bunch of wrapper scripts and which will convert your XSA file to a specific system device tree files. And I've linked to the repository with the README, and it has the nice instructions to convert an XSA to the system device tree. And the next prerequisites is like you need to have the POCI layer, meta-open embedded, meta-virtualization, meta-ARM, meta-Zephyr, and meta-Xilinx layer to be cloned. Why we need like meta-virtualization and meta-ARM is like the system device tree can't be used directly as it is for any of the build system. It has to be pruned to an operating specific device tree, right? And the pruning tool, which is the lopper, is just part of the meta-virtualization layer. And also, like we also depend on like meta-ARM because of the build infrastructure for like meta-Xilinx. So once you have the all the layers cloned, you can initialize the build system using the OE init build environment script from the POCI. And once you have the build system initialized, you can start adding all the layers such as like meta-open embedded, virtualization, ARM, meta-Zephyr, and meta-Xilinx layer using the bit-bake layers, add layers commands. Here is a set of commands you need to run in order to set up the Yocto Project system device tree builds. So most of the layers you can clone from the ScarCap release. For the AMD Zephyr, you have to clone using like the ScarCap next release from the GitHub repository. So we have cloned the repositories. We have the XSA file and the system device tree file. Now we will walk through how we convert the system device tree file to an operating specific device tree files using lopper. The first thing is like you need to clone the lopper and export the device tree flags, compiler flags. And once you export the DTC flags, you transform your device tree to like Zephyr board DTS, a SOC config file, and SOC Kconfig defconfig files. And the lopper transformation can be done in like two ways. One is the manual transformation, and the next one is the automated transformation. For an automated transformation, we use a tool called like generate a machine configuration file. So this gen machine conf, what it does is like it takes your system device tree as the input, and then it will convert to an operating specific device trees, Kconfig, and the defconfig files. In this session, we're gonna use the lopper transformation for like KCU 105. So first thing is like you need to clone the lopper tool from the repository, and you need to specify the lopper output directory and the system device tree output directory and the system DT file. Basically, this DT file will be used as your board DT file. And the next one is the config DT is the one which we are going to use for the Zephyr board DTS. So once you configure your repository for the lopper, right, you need to export this commands and run this lopper command. Basically what it does is like it takes your system device tree and it will use the generate domain DTS lops assist, and it will using the RISC-V MicroBlaze lops, and it will convert to your something called as like system domain DTS. What the system domain DTS is like, you have a processor instance of a device tree for like MicroBlaze RISC-V, and it also includes the additional like programmable logic device tree DT nodes. And once you take the system DT file, which is the domain DT file, and it will generate C flag. Basically, this C flags contains all your processor tune files, which is required for the Yocto project build system. So this is the C file right now. Like it doesn't generate on the lopper output directory. It is generating in the like current working directory. So this will be like fixed soon. And if you look at the output of this C flags YAML file, which contains all the RISC-V ISA tune settings, which is required for the Yocto project builds. And once you have this like domain.dts and the C flags, and then you run through the lopper assist files, and then you can generate something called as like system zephyr.dts. Basically, this DTS file is the output of your system device tree to an lopper transferred for like the Zephyr board DTS. Also, we have one more step if you need to run is you need to convert this system Zephyr DTS to a board DTS, especially when you have an interrupt controller. So the MicroBlaze RISC-V doesn't have a built-in interrupt controller, but Zephyr builds expects an interrupt controller processor node to be present in the board DTS, and below lops file, what it does is like it creates a dummy interrupt controller node inside the CPU, and this will be used for the Zephyr builds. And once you have all the transformation files generated, this is the output of your lopper transformation looks like, which will be used as the input to the Yocto project builds. So this is the like sample machine configuration file like for Zephyr build using like System DeviceTree. Basically, we set the default tune and we include the tune file from the Pocky layer for the RISC-V 32. And also like we set the toolchain library to like newlib. And also you can use like a muzzle in Yocto project to build the Zephyr applications. But glibc is not supported for like Cortex-R and the MicroBlaze RISC-V. And here we use the distro as the AMD Zephyr distro because the Yocto project's cart gap meta-zephyr layer doesn't provide the SCART gap, doesn't provide the Zephyr LTS3 release. And once you have generated these DTS files, Kconfig and the defconfig file, you have to use these variables as an input to the files. And you can assign these variables with the absolute path or the relative path to the files. And you can set the Zephyr board as the board directory structure of your Zephyr project. Basically, your machine configuration file should match with your board directory structure, which is your board name. So if you are having a different name in your machine configuration file, what the meta-zephyr does is like it will take your machine configuration files and it will remove all the underscores and it will convert to the Zephyr board DTS, Zephyr board directory structure. And this is the system DeviceTree file for the multi-configuration MicroBlaze-V file. Basically, you have a MicroBlaze machine file. For example, we are taking the KCU 105 MicroBlaze here. You again like set the default tune files and the toolchain library, and also you need to set something called as like bitbake multiconfig. So in this, we have the bitbake multiconfig example file as like a MicroBlaze-V file, KCU 105 SDT test. On the right-hand side, you can see how the system device tree looks like for the multi-configuration file. Next is the automated transformation for the system device tree to the operating specific device trees. This is done using like a tool called like generate machine configuration file. So we use the system device tree as input, run through this gen machine conf tool, and we generate the Zephyr board DTS, SOC Kconfig, and the def config files. And once these files are generated, automatically it will be generated in your conf directory, or you can specify it to your vendor layer or the custom layer. And in your vendor or custom layer, these files will be generated under conf directory. And once the machine files and multi-config files are generated, this will be used for the Bitbake multi-config builds. And this automation is still in process. It will be coming in this fall release. So here is an example of the Yocto Project System DeviceTree Zephyr recipe. So the template looks like, for example, you have the sample application of like a Zephyr CPP hello world, right? Like you create a, you can create the recipe under your like custom layer, or you can create inside the meta-zephyr core layer as well. So in this example, I'm taking, we are creating a recipe for inside the meta-AMD Zephyr layer. So this Zephyr CPP hello world.bv file, basically it inherits the Zephyr AMD Zephyr SDT BB class, and also it requires the Zephyr AMD Zephyr kernel sourcing files. And here we set the source directory as your like Zephyr base. Basically this points to your cloned Zephyr repository, and inside a Zephyr repository it points to the sample CPP hello world. That is the source you need to set in the source directory. And optionally you can add this compatible machine, where you can set this compatible machine to be built for a particular machine file. And on top of that, you can add the additional extra OE CMake flags. You can specify any CMake flag which is required to build your application. So what you have, like use like system device tree build for existing recipe, right? Like meta-zephyr ships with like a few example recipes like hello world, philosopher, and synchronization. And you need to create the BB append file for these recipes in your custom layer or the meta AMD Zephyr layer. And you have to inherit the meta AMD Zephyr SDT BB class and include the kernel source inclusion file. With that said, like it will build the system device tree for your Zephyr applications. So once you have the recipe created for your Zephyr application, you can configure your application using menu config. And meta-zephyr provides this feature, like it uses the config tool and it will generate the menu config, and user can select, enable, or disable the feature, and the final configuration will be generated in your work directory as the .config. And this .config will be used for the Zephyr application builds. So this is the example how you run Zephyr builds for a particular machine and the target application. For example, here we are using the machine name as MicroBlaze-32 KCU105 system device tree, and then followed by the bitbake command, and you can run the Zephyr application recipes. And also, like on the right-hand side, you can see how you will run the multi-config builds for like MicroBlaze V32. Basically, you have your MicroBlaze RISC-V machine file, and you will have a multi-config file for the KCO 105, and you use like bitbake followed by multi-config colon, and you need to specify the multi-config target name and the multi-config followed by again with the application recipe. And once the build is completed, the images will be deployed in your deploy directory. And in case of multi-config, it uses the current bitbake current multi-config followed by the deploy directory and the machine. So basically, we can't use like a single temp directory to build like machine target images and the multi-config target images. So that's the reason we need to have a separate temp directory for the multi-config builds. So once you build the Zephyr application, so how do you run this Zephyr application on a board, right? So basically you source the Vivado tools and you program the bitstream and you select the target as the RISC-V user tool and you can program the bitstream. And once you program the bitstream, you reset the processor and then you download your Zephyr applications, and once it is downloaded, you should be able to see up and running on the target. So right now, like we do have some limitations in the meta-zephyr and the meta-AMD Zephyr. Meta-zephyr's CartCap release doesn't support the Zephyr LTS 3.7, and we are working with the Zephyr community, meta-zephyr community to backport this SCARTCap with the LTS 3 release. And also, like if you want to build the Zephyr application outside of meta-zephyr core, today it's highly impossible because it depends on the Zephyr image include file, which exists only in like meta-zephyr core layer. And if you're having a recipe outside of this core layer, you can't really build it. Basically, what we are planning is we are planning to convert this inclusion file to a bitbake class so that you can inherit those class from your custom layer or the distro layer. And also the Zephyr, meta-zephyr OS output files doesn't have any of the image artifacts, such as it doesn't include any of your machine name, your like timestamp for the build help files, all those things. Basically, it contains like Zephyr hello world.help. And the next thing is like meta-zephyr doesn't support the board extension builds. For example, if you have your own board builds, you can't use it, and that is something we are working with community to support in long term. And in case of meta-zephyr, meta-AMD Zephyr, it has limitations like such as it doesn't support like Yocto Project run QEMU for the running all the Zephyr application. And also it doesn't deploy all the MicroBlaze bitstream files and the DeviceTree files, which is required for the QEMU boot. Cool. This is the next roadmap for the meta-zephyr layer and the meta-AMD Zephyr layer. Oh, sorry, we are almost out of time. If you have any questions, we can take it up. Yes, Mohammed. Because the meta-zephyr SCARTCap doesn't support the LTS release.
I understand about the Octaler, but you said you have a...
Oh, the fork the thing is like we do have the MicroBlaze 32 and the Cortex R52, which is not yet upstreamed. It is in the master layer, but not in the Zephyr LTS 3.7. Yes, we do have some plans. But it might take some time. Yeah. Can we get some mic?
Hello.
Yeah. Go ahead.
So you use Yocto to build Zephyr, so that means that on the SoC have another Linux core, right? So if you build the application, the smaller microcontroller with Zephyr only, so probably you don't need the Yocto to build it, right?
Sorry, can you repeat the question?
So you use Yocto layer to build the Zephyr, right? Yocto project to build Zephyr, right? So for the smaller application, right? So you don't have the Linux core. You have only microcontroller only. So is that Yocto is overkill?
It's not like overkill, like it has a purpose, right? For example, if you are building for like a heterogeneous build system where you have building like, if you are using like one build system to build like Linux image, bare metal, and FreeRTOS, then it makes sense to use like one build system, right? For example, in our case, when we build the Zephyr application for an Cortex R52, right, we package to the our boot.bin, which is the bootloader, and we program it directly. And you can execute in parallel for APU will be running with Linux, and the RPU will be running with Zephyr RTOS.
Okay, thanks.
Sure.
Curious if the MicroBlaze-V core supports remote proc, or if there's any intent to support remote proc, so that you can run your MicroBlaze-V core from Linux.
As of now, like we don't have any support to run remote proc on MicroBlaze-V.
Is that intended? Do you have any roadmap for that, or no?
We don't have roadmap. We do have our marketing folks here. They can take up the question. Yeah, go ahead.
Where do you, like, how do you find SDTs? Like, is that something you already have in your layer as samples, or?
Yes.
Okay.
We do have some. We haven't upstream those changes. It will be coming in fall when we roll out with the Gen Machine Conf. We will upload all the SDT files in our Artifactories.
But then, like, the same principle should be applicable to other kind of SoCs that have like an M and an A core, right? So you should.
Yeah, you should be able to use it, because the way the lopper is written is, it doesn't look for the proprietary tools, right? All it needs is the input as the device tree. Whatever you write in the device tree, it will take, it prunes, and it generates the output artifacts. Thank you.